Hi, everybody, and welcome to part 2 of Unit 1, Lesson 12. In our previous video, we went through the definition and the examples related to intermediate value theorem. And in this video, we're going to be going through some practice problems that require us to use the intermediate value theorem. So when we look to apply the intermediate value theorem here, there are going to be 3 steps to how we do this problem. The first step is going to be to check the conditions. If you think back to what we went over in our previous video, there are 2 conditions we need to use before we can apply the intermediate value theorem. There are 2 conditions we need to verify and criteria we need to meet. And those conditions would be we need to have a function that is continuous, and we need to have a k value that we're trying to verify that is between f of b and f of a. Once we've checked those conditions, the second step is going to be to explain our reasoning. And to explain our reasoning, we need to explain that we checked these conditions and they were both correct. They were both satisfied. The third step is going to be to state our conclusion. So once we've checked to see that our conditions have been met and we've explained that we met those conditions, we then need to state the conclusion that we're allowed to draw using the intermediate value theorem. So while we're doing these problems, I want you to keep in mind that we are always going to follow these 3 steps. An example problem that we're going to start with here says, suppose f of x is equal to 25 minus x squared. Can you guarantee a value c where negative 2 is less than c is less than 6 such that f of c is equal to 0? Justify your answer. The first thing I want to point out here is that I would know that this was an intermediate value theorem question because the question is asking me, can I guarantee a value such that it has a particular output value for that input value? So can I find an input value c where when I put that into the function, I have a particular output? Anytime we are asked to guarantee a particular output, that's going to be an intermediate value theorem question. Now that means we need to go through the process of checking the conditions. The first condition that we need to check is our function continuous? So in order to check whether our function is continuous, the best way to do this is to go to the definition of the function or the directions for the problem. Since our function is f of x equals 25 minus x squared, we can say yes, this is a continuous function because it's a polynomial. Now, I know that it's a continuous function because polynomials are not going to have any discontinuities. They're not going to have any jumps, infinite discontinuities, removable discontinuities, anything like that. The second condition that we need to check is our k value. In this case, our k value is 0. So this k that we're trying to guarantee is 0. Is that value in between f of a and f of b? And as a reminder, a and b are the x values that are given as the boundaries for c. In order to check this condition, I would highly recommend sketching a picture. So to check the second condition, sketching a picture is your best option. Now, it doesn't have to be a detailed or perfect picture. So the first thing I would do is just sketch a quick graph. I know that my x values that I need to highlight on my graph are negative 2 and 6. So what I'm going to do is just sketch a quick little graph here where my x values go from negative 2 to 6. Now, this is not going to be a graph that's drawn to scale or anything like that. It's really just to help me visualize what's happening graphically. Now, we want to check to see if our k value, our 0, is in between the outputs. So in order to do that, we're going to have to start by finding the outputs. So I'm going to find f of negative 2, which would be 25 minus negative 2 squared, which is 25 minus 4, so 21. And I'm going to find f of 6, which is 25 minus 6 squared, which is 25 minus 36, so negative 11. So on my graph, I'm going to go ahead and I'm going to graph those points. I know that my y values are negative 11, and that happens when x is 6. And I know that my other y value is positive 21, and that happens when x is negative 2. So I've got 2 points on my graph. Now, although the shape of this graph would not be a straight line, we don't really need to think too much about the shape. So to analyze whether I can have a y value of 0 or not, all I'm going to do is choose to connect my points in the simplest way possible. I'm not going to worry about whether it's curved or straight. I'm just going to make a straight line because that's the simplest kind of graph I could draw. Now, what I want to check is this y value of 0 in between the two y values on my graph? Well, a y value of 0 would be here on the graph along the x-axis. So based on what I'm seeing here, yes, this graph would have to cross through that line because 0 lies between negative 11 and positive 21. So by doing this, I can visually check the second condition. Is our k value between the y values of the two endpoints? Now, the second step of this problem is going to be to explain our reasoning, and that means we have to kind of explain in words what we just quickly jotted down to check our reasoning. So if we want to use the IVT to justify our answer, here's how we do that. We're going to start by saying, since f of x is continuous. And I'm allowed to say that because I checked, and that was the first condition that I checked here, that this is a polynomial. And 0, so the number that I'm trying to verify, is between f of negative 2 and f of 6. So that's the second condition I checked. 0 is in between these two numbers. Since these two things are true, that's my reasoning. I've checked the conditions. Now, what can I say as a result of that? So what is my conclusion? My conclusion is the answer to this question. Can you guarantee a value C? We would say, we can guarantee a value C where negative 2 is less than C is less than 6. You'll notice I'm just answering the question by copying it down as a statement instead of a question. Can you guarantee this? Yes, we can guarantee a value C where negative 2 is less than C is less than 6, such that f of C equals 0. So this statement right here is the conclusion that I need to state. So can you guarantee this? I can guarantee this. So since f of x is continuous, that's the first condition. The second condition is and 0 is between f of negative 2 and f of 6. We can state our conclusion. We can guarantee a value C where negative 2 is less than C is less than 6 such that f of C equals 0. And then this is the really important part. We need to say why, which means we need to reference the theorem we're using. So we can say by IVT. Now that by IVT is what tells us that these two conditions satisfy the intermediate value theorem, so we can draw our conclusion using that theorem. So since these two things are true, we can make this guarantee using the intermediate value theorem. Okay, let's try another one. So suppose f of x is equal to 25 minus x squared. Can you guarantee a value C where 2 is less than C is less than 5 such that f of C is equal to negative 3? Justify your answer. Now you'll notice we have the same function here that we did in problem number 1, we just have a different interval. So it's going to force us to really reanalyze the conditions and did we meet them or not. I know that I'm using the IVT here because the problem says, can you guarantee a value C where we have a specific output value? So that's my clue that I'm using the IVT. The first thing I need to check is, do I have a continuous function? That's always the first condition. That's what I'm asking myself. Is this function continuous? The answer here would be yes, because this is a polynomial and polynomials do not have any discontinuities. The second thing I want to check is, does my y value, my desired output, live between the outputs that I get when I plug in A and B? So to do this, I'm going to sketch a graph. It helps me visualize whether I've met this condition or not. My important x values here are positive 2 and positive 5. So let's see here, positive 2 and positive 5. Those are my important x values. I'm going to plug those x values in. F of 2 would be 25 minus 2 squared, which is 21, and f of 5 would be 25 minus 5 squared, which is 0. And I'm going to go ahead and graph those points. So I've got the point 2, 21, which is up here, and 5, 0, which is right here. I'm going to connect these points in the least complicated way possible. Although this graph is a curve, I just really need to visualize connecting the points as simply as I can, which would mean using a line. And I want to know if I ever have a y value of negative 3. Now on this graph, negative 3 would live down here somewhere. So I want to know, can I promise I cross this line? Well, clearly that line is not between the y values that I have. I don't know for sure that this graph crosses this line based on the information that I have. So because of that, I would say, well, no, I can't guarantee this. So here's how we explain our reasoning when the IVT says, well, we can't make any guarantees. The first thing we need to do is say since, and then tell me what's wrong. I know that f of x is continuous, that was fine, but what's wrong here is that negative 3 is not between these two numbers. So I would say, since negative 3 is not between f of 2 and f of 5, we cannot guarantee a value C where 2 is less than C is less than 5, such that f of C is equal to negative 3. And that's all we need to say. Since we did not meet one of the conditions, and we need to specify which condition that is, we cannot make this guarantee. And we're not going to say here by IVT because we're not applying the IVT. We can't use the intermediate value theorem if we don't satisfy both conditions. So I'm just going to say, since I didn't satisfy the conditions, I cannot make this guarantee. All right, let's look at a slightly different type of question. So problem number 3 says, a car travels on a straight track. During the time interval from 0 to 60 seconds, the car's velocity is measured in feet per second, and it's a continuous function. The table below shows selected values of the function. And part A here says, for 0 is less than t is less than 60, must there be a time when the velocity is equal to negative 5? So it's asking me, can you guarantee, must there be a time when I have this particular output? And I've got a table of values with those outputs in it. I can tell here that I need to use intermediate value theorem thinking in order to make this guarantee because I'm asked to guarantee a specific output. One of the strategies that I would use here to solve this problem is I would sketch a graph of this function. Now it looks like my t values need to go from 0 to 60, and my velocity values, which in this case are my y's, need to go from negative 30 to positive 10. So I'm going to go ahead and sketch a graph that shows the first and the fourth quadrant. I'm not going to worry about quadrants 2 and 3 since I've only got positive time values. So on the x-axis, I'm going to have the numbers 0 and then 15, 25, 30, 35, 50, and 60. And I'm just sketching a rough graph. You'll notice these are not evenly spaced. I'm not worried too much about that. This is not part of explaining my reasoning. This is just getting a visualization so that I have a good idea what's going on. Now my y values, I'm going to need the important numbers negative 20. I'm going to need the important number negative 30. I'm going to need negative 10 and negative 14. I'm going to need 0 and I'm going to need 10. Now, if I sketch a graph of this, I'm going to go ahead and just sort of connect the dots here. So my graph is going to look like this: 0, negative 20, 15, negative 30, 25, negative 20, 30, negative 14, 35, negative 10, 50 is 0, and 60 is 10. And I'm just going to go ahead and connect these dots with a straight line between each of them. Now the problem is asking me, will there ever be a time when my velocity is negative 5? Now negative 5 would be here on the graph. So what I'm really asking is, will you ever have to cross this line? Well, the answer is yes. I would definitely have to cross that line, possibly more than once, but for sure at least once. And that would have to happen between 35 and 50, which makes sense because negative 5 falls between negative 10 and 0. So I would say, yes, there must be a time t when v of t is equal to negative 5. Explain your reasoning? Well, it's because negative 5 lives between these 2 points on the graph. So that's how I'm going to explain my reasoning. The justify your answer and the explain your reasoning part are kind of where I use the theorem. So I would say, since v of t is a continuous function, and I know that because it said so in the instructions that v of t is a continuous function. And that's the first condition of the intermediate value theorem. The second condition is, and negative 5 is between v of 35 and v of 50. So since I've met these two conditions, I can say the same conclusion I did in part A. There must be a time t when v of t is equal to negative 5. And I can say this by applying the intermediate value theorem. And that's kind of the third part of your reasoning. Now, this often comes up on the AP test as part of multiple choice questions. So let's look at a couple different examples of multiple choice questions that you might see. For problem number 4, it says, consider the continuous function f of x on the table below. And you'll notice it's telling me in the instructions I have a continuous function, which is one of our conditions. If the intermediate value theorem is applied from negative 4 to 4, what is the minimum number of zeros for the function on the interval? Now, the number of zeros means the number of times that y, or f of x, has to equal 0. So zeros are when the outputs are 0. Again, I think that graphing this is a really great strategy for thinking through this question. Anytime you can visualize your thinking and represent it in multiple ways, it's going to be really helpful. So I'm going to go ahead and sketch a graph of what I've got going on here in this table. My table goes from negative 4 to 4 on the x-axis and negative 2 to 0 on the y-axis. So I'm going to go from negative 2, negative 4, zeros in the middle, and then we've got positive 2 and positive 4. And then here on the y-axis, we've got negative 2, positive 1, zeros in the middle, and then 1 again, and then negative 2. Now, if I were to graph this, I would have negative 4, negative 2, negative 2, comma 1, 0, 0, 2, 1, and 4, negative 2. So if I were to connect that with straight lines, and again, I don't know if this is straight lines, but it's the easiest way to connect the dots to get a quick visual, it would look like this. How many zeros do we see? Well, again, zeros are where the y value is 0, which is this x-axis on the graph. How many do we have to have? We have to have 1, 2, 3. One of them is guaranteed because that's actually in the table. And the other two make sense because 0 is between negative 2 and 1, and 0 is between 1 and negative 2, and I can visualize that on the graph as well. So that means I'm going to be able to guarantee at least 3 of these zeros. For problem number 5, it said let g of x be a continuous function. Selected values of y equals g of x are given in the table. For which value of k will the equation g of x equals 1 have at least 2 solutions on the closed interval? Again, I think that graphing here is going to be our best bet, and we're looking for 2 solutions to this equation. So we want the y value to equal 1 twice. All right, now we've got a table of values where one of our values is missing. So let's graph what we know for sure. Our x values go from 2 to 8, and our y values, the lowest is 2 and the highest is 5. So on our x-axis, we've got 2, 3, 4, 5, 6, 7, and 8's way over here. On our y-axis, we've got 1, 2, 3, 4, and 5. Now here's what we know for sure. We know that the point 2, comma 3 is on the graph. We know that the point 3, comma 4 is on the graph. We don't know what the y value is for 4, but we know that 5, comma 5 is on the graph and 8, comma 2 is on the graph. So we know for sure we can connect these dots and these dots. The question is, where does this point at 4 go? One of our potential candidates is for 0. So if we make this k value 0, that would put the point right here, which means our graph would get connected like this. Now let's ask ourselves, how many times is our y value 1? So our y value being 1 means we want to cross this line in 2 spots. Well, based on this graph, it seems like that happens. I've got 2 output values, but let's just be sure by checking our other answer options. If we make our y value 1 instead, then we would have our point here instead of here, and so our graph would get connected like this. Well, that graph does touch the green line, but only in one spot, so it doesn't quite match what we were hoping, which is 2 solutions. If we make our y value 2, now we miss the green line completely, and we don't have to cross that line at all. And if we make our y value 3, again, we miss the green line completely, and so we don't have to cross that line at all. And what that means is that the only way to get 2 solutions and guarantee that would be to make your y value 0. Another example of this kind of problem is a problem like number 6, where it says the function f and g are continuous for all real numbers. So it's telling me in the directions I've met one of the conditions. I need to have a continuous function. The table below gives values for selected values of x. The function h is given by h of x equals g of f of x plus 2. Explain why there must be a value w between 1 and 6 such that h of w is 0. Now, by reading this question where it says, explain why there must be a value, so explain why we can guarantee a certain output, I know that that means I need to use the intermediate value theorem. Now, in order to do that, I need to check my conditions first. The first condition I need to check is, do I have a continuous function? The answer is yes, and it says so in the instructions, so I don't have to really worry about that. For the second condition, I need to kind of visualize what's happening on the graph. I know that my x values that are important are 1 and 6. So I know that my important x values are 1 and 6. And what I'm going to do next is substitute those values into my function so that I can find the y values. So I'm going to find h of 1, which would be f of g of 1 plus 2. Now, in order to evaluate this, I'm going to use the values in the table. So in the table, I can see that g of 1 would be in the g of x row when x is 1 is 3. So I'm going to have f of 3 plus 2. F of 3 would be in the f of x row. Find the output when x is 3. Oh, I wrote this backwards. I'm like, why am I not finding these values? I wrote it backwards. It should be g of f. I apologize, everyone. F of 1 is 2. So let me just change this really quick. There we go. Now it makes a little bit more sense. G of 2 would be negative 12. So I'm going to have negative 12 plus 2. And so I get negative 10. That's my first output value. So when x is 1, my y value is negative 10. And when my input value is 6, h of 6 would be g of f of 6 plus 2. F of 6, I'm going to go to my table, is 8. So I'm going to have g of 8 plus 2. G of 8, I'm going to go to my table, would be 28. So I'm going to have 28 plus 2, which is 30. And 30 would be up here on the graph. Now, if I connect those 2 points with a straight line, because that's the simplest way, the question I need to ask myself is, can I guarantee or explain why there must be a value where my output value is 0, which would mean I'm crossing this orange line? Well, I can definitely say that it's true because we've satisfied both of these conditions. So this is the part where we need to explain our reasoning. First, we need to state that we satisfied both conditions. So we would say since, first of all, h of x is continuous, and second, the number 0 lives between these two numbers, which are, oops, not f, h of 1 and h of 6. Now we're going to use the wording of the original question as our conclusion. There must be a value w for 1 is less than w is less than 6, such that h of w equals 0. And we can say this using the intermediate value theorem. All right, last but not least, we're going to do one more example, and it's very similar to the example we just did, where you're given information in the directions and just asked to explain why it must be true. So number 7 says let f be a continuous function, and then it gives us 2 values of f. F of 2 is 5 and f of 5 is 2. Let's let h of x be f of x minus x. Explain why there must be a value r, where r is between 2 and 5, such that h of r is equal to 0. Now it's saying here, explain why there must be. So explain why we can guarantee a certain y value. And that's what tells me that this is an intermediate value theorem question, which means I need to follow my 3-step process. First, check the conditions. Is this a continuous function? Continuous. O-U-S. There we go. I'm like, that did not look right. And yes, it's a continuous function, and I know this because it tells me in the directions that f of x is continuous, so is x, therefore f of x minus x is continuous. Number 2, check your output values, which means we're going to sketch a quick graph to give us a good visual. So my x values for this graph are 2 and 5. And again, I know that because that's the boundaries of my r, which is an x value. So I've got 2 here and I've got 5 here. Now I'm going to find my output values. So h of 2 is equal to f of 2 minus 2. Now, f of 2 is actually something that I have from the instructions. It says here f of 2 is equal to 5. So I'm just going to go ahead and use that information. F of 2 is equal to 5. And I'm going to substitute that. F of 2 is 5 minus 2, which gives me 3. So my first output value is 2, 3, which is here on the graph. Next, I'm going to find h of 5, which would be f of 5 minus 5. And again, f of 5 was given to me in the instructions. F of 5 is 2, so I would have 2 minus 5, which is negative 3. So on my graph, I'm going to find the negative 3 and graph it, 5 comma negative 3. And I'm going to connect those 2 points with a straight line just to get a visual of what points I'm guaranteed to cross through. Now, having a y value of 0 means crossing this line right here, which I can definitely say that I do because that line is within the y values that I calculated. So now we just need to explain our reasoning. We start explaining our reasoning by stating that we've satisfied the conditions. So we would say since, number 1, h of x is continuous, and number 2, 0, the number I was trying to guarantee, is between h of 2 and h of 5. Now I'm going to use the wording of the original question as my conclusion. I'm going to say there must be a value r, blah, 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 blah. So I'm going to say there must be a value r for 2 is less than r is less than 5, such that h of r is equal to 0. And then I need to state that this is because of a specific theorem. So I would say by IVT at the end. Okay, thank you guys so much for watching, and I look forward to seeing you soon for some more practice.